Quantum computing. You've heard the term, right? It promises this revolution on a scale that's almost impossible to wrap your head around. But what if that future isn't decades away? What if we could start building a bridge to get there, right now, with the tools we already have? So how do we do it? Let's explore how we can lay the very first stones on that bridge, starting today. See, on one hand, you've got this incredible dream. The promise of quantum computing is huge, curing diseases that we've given up on, designing revolutionary new materials from the atom up, tackling these massive global challenges that our best supercomputers can't even touch. But then, you hit the reality of it. The hardware, it's still basically in its infancy. Programming these things is mind-bendingly complex. The whole field kind of feels stuck in the mud. So, how do we get from here to there? From the reality to the dream? Well, what if the answer isn't just to wait around for a miracle? What if we build a bridge instead? And this is the core idea, the really brilliant part. We don't have to wait for some perfect, all-powerful quantum computer to appear. We can actually start tapping into its power today with a really clever new strategy. And here's the plan. It's basically a two-step process. First, you have to make quantum computing accessible. You teach it to speak a human language so that anyone, not just a handful of physicists, can actually use it. And second, you stop trying to boil the ocean. You focus on building practical prototypes that solve very specific, high-impact problems right now. That way, you prove the value of this whole approach long before the hardware fully matures. Okay, so how does this bridge actually get built? Well, the heart of this whole strategy is an incredibly powerful AI-powered simulation engine. It's a system that can mimic a quantum computer, but it uses technology that's already sitting in data centers all over the world. So let's pop the hood and break down its key parts. So the first piece of the puzzle is the LLM interpreter. Seriously, think of it like the universal translator from Star Trek. You can literally type a command in plain English, something like, hey, link 3 quantum bits together in an entangled state and then measure the result. And boom, the large language model instantly converts that simple sentence into the super complex sequence of quantum operations needed to make it happen. It's basically zero-code quantum programming, no PhD required. But what is this AI actually talking to? Well, that brings us to the magic square model. This is the core of the engine. It's a powerful mathematical framework that acts like a highly detailed digital twin for the quantum world. It's uniquely good at simulating the incredibly complex, frankly weird behaviors of subatomic particles and chemical reactions, which is exactly what quantum computers are supposed to be great at. And the engine that drives all of this, the raw horsepower, is the GPU. Yep, the same kind of chip that powers high-end gaming and all that AI training you hear about. It provides the massive parallel processing power needed to make these incredibly complex simulations just fly. And the payoff in productivity, I mean, wow. It is absolutely staggering. Just look at this table. Simple, fundamental quantum tasks get this massive speed up. Preparing a basic entangled state, a Bell state, goes from 3 minutes of manual coding to just 8 seconds. A key quantum search algorithm, that drops from 15 minutes to 23 seconds. And look at this last one. A complex molecular simulation setup goes from a full hour of painstaking work down to just 2 minutes. This isn't just a little improvement. It's a total game changer for making this stuff accessible. And it's not just about saving time for the programmers, it's about raw performance. This engine can simulate a simple water molecule almost 4 times faster than the traditional methods. That is a huge leap in computational efficiency. Okay, so the engine is fast. It's easy to use. Great, but what can it actually do? What's the point, right? This is where we shift from the nuts and bolts to the real-world impact. Let's see what happens when you actually point this power at some of science's toughest problems. Let's start with drug discovery. To simulate a key chemical reaction in the human body, a process that used to seem impossibly complex, this new approach can get it done with the number you see right here. 3. That's it. Just 3 simulated quantum bits is all it takes to model this thing called the proton tunneling effect, turning what was a monumental challenge into something totally manageable with the tech we have today. And here's why that matters so much. By accurately simulating this one tiny quantum effect, we can get a much better understanding of how drugs will interact in the body. And the potential payoff here is mind-blowing, accelerating the entire drug discovery process by more than 1,000 times. Just stop and imagine what that means for medicine. All right, next up, let's look at materials science, specifically the hunt for new superconductors. The predictive power of this model is just stunning. For a whole bunch of different materials, its predictions for their critical temperature, the point where they become superconducting, are within 5% of what's been measured in a real lab. That is phenomenal precision. And because the model is so fast and so accurate, it completely flips the discovery process on its head. Instead of slow, expensive trial and error in a laboratory, you can now screen new potential materials 60 times faster. This just dramatically speeds up the search for these world-changing materials. Now, these prototypes are incredible, but they really are just the beginning. They're like the first structures we're building on our bridge to the quantum future. The ultimate vision is something even more profound, a truly adaptive quantum system. This next big step is called FAQS 2.0, a fully adaptive quantum system. The idea is to build a system that isn't just programmed, but one that can actually adapt on the fly. It would correct its own errors, it would reroute computations, it would optimize its own resources in real time. We're essentially talking about a self-optimizing quantum brain. So we have the bridge, that AI-powered simulation engine. We have the destination, a fully adaptive quantum system. But there's one more piece to this puzzle, a single breakthrough that could take this entire roadmap and just throw it into hyperdrive. And that final piece is room temperature superconductivity. If we can create materials that are superconducting without needing to be cooled down to nearly absolute zero, it changes literally everything. It's a technology that would take quantum computing out of these massive, crazy expensive laboratory refrigerators and turn it into a general-purpose engineering component you can actually build with. And what's so powerful is this gives us a clear three-stage path forward. Right now, we build these valuable AI-powered prototypes. In the midterm, those will evolve into the first adaptive FAQs 2.0 systems. And then, in the future, a breakthrough and room temperature superconductivity could let us build massive, powerful quantum data centers. And the difference? I mean, just look at this. It would be night and day. On the left, you see today's reality. A single quantum processor hidden inside this massive, multi-million-dollar dilution refrigerator. On the right is the future that RSTC enables. A simple, powerful quantum chip that can operate right here at room temperature, just like the processor inside your computer. Okay, so let's just pull this all together. Quantum's incredible potential is, right now, blocked by some very real-world limits. But a smart, two-part strategy using AI simulation as a bridge is making quantum power accessible today. We're already seeing this approach solve huge problems in drug discovery and material science, and the roadmap ahead leads us toward these amazing, self-adapting systems, all supercharged by the revolutionary potential of room temperature superconductivity. Which leaves us with one final fascinating question. We are actively building this bridge to the quantum era, using AI as both the architect and the raw materials. The path is actually becoming clear. So, the real question is, what kind of world will we choose to build on the other side?